and the question is asking what's the resultant moment about point O. So we're going to solve this problem using two different methods we introduced. The first method is just a mathematical approach. The resultant moment is moment due to force 1 generated about point O plus the moment generated about point O from force 2, right? So in fact it's R1 cross F1, this is just moment from force 1, plus R2 cross F2, moment coming from force 2, right? This is the first method we consider. So this is a direct approach. You get the value of position vector of the force, plug into the determinant, and then the end result is the moment at point O, the resultant moment of these two forces at point O, right? The second method was what? Method of moving forces. So what do we do in the moving forces?
Forces.
Huh?
Put things in perpendicular.
Yeah, break it down. The first step was decompose or break it down. The second step was move along the line of action, right? The third step was just get the moment arm, multiply the force, and take your right hand to say it's positive or negative, right? So we did that in 2D. We saw lots of examples. When I say lots, it's just 2, right? But, or maybe 3. But we're doing it in 3D today. We want to see how that procedure works in 3D, right? So let's first do the method of moving forces, right? So the first step is break it down, right? So if I break this down, you have in the J component is 40, right? In the X component, negative 60. In the K component, positive 20. Right? So as you can see, this is already decomposed because they give you the Cartesian form of vector force vector. If they give you a force magnitude with 2 angles, what you can do use projection or cosine angle to find all the components. But right now they simplify your job. They just give I, J, K component of force. So you just put it like that. Decompose every force. Step 1. Decompose all forces to X, Y, Z component. Now let's go to this guy. This guy has 80 I, 40 J, negative 30. Just put some 30 here. So negative 30K, 40J, and 80 I. So this is the first step, decompose it. Now the second step, move each force so that it becomes perpendicular with reference axis or point. Now, in this case, we have 3 axes, X, Y, Z. In 2D computation, we were looking from the above. So we only had one Z axis, right? The moment was either positive K or negative K. And because we were looking above, the axis was just like a point. We couldn't even see the line axis, right? But in 3D, you see Y axis, X axis, Z axis. So what we need to do is to consider each axis independently and find the component of resultant moment around that axis. So let's start with axis X. So moment resultant about axis X. So now let's consider this axis, right? And move the forces. So let's start considering this axis. So I say moment resultant about axis X. And then I go over all the components and I try to move them to find the moment arm, right? So let's start with this guy, 20. Should I move it with respect to the x-axis? Should I move it? It's already normal, as you can see, orthogonal. So what's the moment arm?
5.
from here to here, which is from here to here, which is from here to here. You see, this is perspective drawing. So it's 5 times 20. Let's write it here. 5 times, this is call it back. 5 times 20. Positive or negative? Positive. Now let's go to this guy, 40. The question may be, I think you may have a question, why is positive? Right? Well, take your right hand, right? Finger goes through arm. This is the position vector from reference point to the point that force is acting on, arm. The palm will be showing the direction of force, up. Right? If it was down, you would do this. And then your tongue would be showing positive X in 3D space. So it's positive. Right? Now let's go to this guy. Where should I move it?
Back.
All the way back. But look, if you move it here, you can see that it's going through that axis. So the moment arm is 0. Right? This is called concurrent force. It's going to the reference point. No matter how many force we have, if they pass through that point, the moment of all of them is 0. So later on in this course, you will see that we're trying to find the reference point that most of the force on the system are passing through that point to write our moment equation when we do equilibrium, because that greatly simplifies the computation, the task. So the first category of exception is concurrent forces. You just don't do anything, it's 0, you just skip it. So the moment you see this guy is going through that, the moment is 0, just skip it, go to the next one. What about this guy? Can it generate a rotational effect around axis X? This is parallel to this line. You see, it can generate a rotation about Z. You see that? It can, but it cannot generate a rotation about the x-axis, because what? It's parallel to x-axis. So the moment, the angle, you remember we said R cross F is the magnitude of R, magnitude of F sine theta, that angle theta is 0. They're parallel to each other. So the moment is 0. So the second category are parallel. Parallel, maybe 1R double F. So parallel force. So when you see a parallel force, immediately ignore it. The moment is 0. Parallel to the axis is parallel, right? So nothing from 40 because it's concurrent going through that point. Nothing from 60 because it's parallel, right? It's parallel to this. But the 20 gives you a moment arm, and it's positive X, right? So I'm done with this force. Now let's go to the contribution coming from F2, right? Let's go to the AT. What do I observe?
Parallel.
It's parallel, this category, right? So just ignore it. You cannot generate any rotation. Always ask this question, can you generate a torque of rotation about the given axis that I'm considering? If the answer is yes, then go find it. If the answer is no, then just skip it, right? Now let's go to this force, 40, with respect to axis X. So what should I do? Step 2, move it. Is it parallel to this axis? No. Is it going through that axis? Is it going through? No. So move it. Where should I move it? Here or here? Left. You move it all the way, so you put it here. And here is orthogonal, 40. So that's your moment arm. So the moment arm is 2. So 2 times 40, positive or negative? Positive. R cross F goes this way. All right. Now let's go to this force, 30, the last one. Where should I move this? First ask the question, is it going through that axis? No. Is it parallel to that axis? No. So you can just skip it immediately, right? So there is some movement, it can generate some rotation, right? As you can see, this thing, if you have weight here, it can rotate around the axis X, right? So where should I put this force? Down or up? Up. So you bring it right here. And then, with respect to this axis, this becomes perpendicular. So what's the moment on? From here to here, which is from here to here, which is from here to here. It's 5. 5 times 30. Positive or negative? Yeah, it's negative. R cross F. What else? What else do I have? What else do I have? That's all, right? I already did this, the 20, the first step. This is parallel, this is concurrent. Then I'll come to here. This is parallel. I did this 40 and I did the 30. So that's it. This is the resultant moment in the x-axis. Because we're going to have y and z-axis. In 3-dimensional, you have 2 results. In 2D, we only have in k. So the resultant moment is either positive or negative. Just one value. What we're trying to find, 3 different components. M resultant x, M resultant y, M resultant z. Right? So this is M resultant x. So let's simplify that. That's going to be 100 plus 80 minus 150. So 180 minus 150 is going to be 30. So the x component is 30. Let's go to the y component. Let's do it quicker than the x. So M resultant y. Now I change my axis to y. Consider axis y. Let's go to this component. Is it going through axis y?
Yes.
Concurrent force. Moment is 0. What about this guy? Moment 0. What about this guy? 0. It both goes through that axis and also is parallel to that axis. So you don't do anything here. Now let's go here. What about 40? Parallel. Don't do anything. Now you have 130 and 180. Where should I move 30 to get the moment on? All the way up to this point, right? So what's the moment on? From here to here, which is 4. 4 times 30. Positive or negative? Huh? So R is from the reference axis to the point that force is acting on. So R is this way. The force is going down, so if you take your right hand, R cross F. So your finger, your thumb would be positive Y. So it's positive. Right? What about AT? Where should I move it? This way or this way?
Back.
Back, yeah, right? Here, you see that? So what's the moment on?
2.
2 times 80. Positive or negative? Thank you. So I did 80, I did 30, this is parallel, they'll all go through that axis, so I'm done. This is the y component. You see how fast it is? It could be even faster. So 120 minus 160 is negative 40. Now resultant moment with respect to z-axis. Now we're considering this guy, this axis, right? Now let's go with this first. We start with this component.
It's parallel.
Parallel, thank you. 0. Skip it. What about this guy?
It's concurrent.
Concurrent. Skip it. What about this guy?
Status. 630.
It's perpendicular already. You don't need to move it, right? So its moment arm is what?
5.
It's from here to here, which is from here to here, which is from here to here, right? Because it's a three-dimensional drawing. So it's 5 times
60.
60. Positive or negative?
Negative.
Look, this guy, this guy has a negative 60 I component. So it is positive 60, negative 60 here, right? So the force is actually going this way in the negative I. So you take your right hand, where is R? R is starting from the reference axis, this is a reference axis, right? And ending at the point that force is acting on. So this is my R. So your finger of right hand goes through R. The palm would be showing force, and the thumb would be showing the directional moment. So what is it? Positive, right? Positive 5 times 60. This is parallel, this is concurrent, we got rid of all these things. Now let's go to this guy. What about this guy? 30, it's parallel, don't do anything. What about this 40? Move it back, all the way here. So what is your moment arm? 4, from here to here, right? 2 is the distance to this axis, but when you move it here, right, this is going to be distance to the z-axis, right? Alternatively, this side. If you draw the three-dimensional box, when you bring it here, right, then from here to the axis, this axis z, you see that? This axis z. This distance is what you want because it's perpendicular to find. So that distance is 4. 4 times 40. Positive or negative? Positive. Now go to the last one, because the 31 is parallel. We don't do anything, right? The last one, the 80, where should I move it?
Back.
All the way back to here, right? So the moment arm is from here to here, which is from here to here, which is 5. 5 times 80. Positive or negative?
Negative.
Thank you. All right, so let's do computation. That's going to be 300 plus 160 minus 400. So that's 460 minus 400, positive 60. Right? So, if I want to write the resultant moment, I would say this is equal to something times x, resultant moment in the xi, plus resultant moment in the y direction j, plus resultant moment in the z direction k, right? And that's going to be, this one is positive 30. So 30i plus negative 40 j plus 60 k. I'll just put the end result there, right? And that's, this method, we use a method of moving forces to find the value. That's the tricky method that we use. Now let's use the direct method. Let's do cross product to find R, and we already have F, plug into cross product and see if you can get exactly the same result or no. This is the final result. Let's see if we can duplicate this using method of, so this method was method of moving forces. Method of moving force. Right? And this is the result. Now for the cross product, the direct method, this is almost done. The cross product. And result is equal to R1 plus F1 plus R2 plus F2. R1, what's R1? R1 is starting from the reference point to the point that force 1 is acting on. So R1 is this guy, which is 5. 5J, right? 0I, 5J, 0K. It's only in the J direction. So 5, so R1 is 5J. What about R2? R2, which one is R2? From the reference point all the way to the point that force 2 is acting on. So this is a different color. This is R2. This is R2. So what's R2? It's 4I plus 5J negative 2K. You see that? This point, with respect to this point, it has 4I, 5J, and negative 2K, because this is on their XY plane, so it's negative. You see that? So all I need to do is to put it in the cross product. So I write here R1, 5J, cross F1. Would you read F1 to me? Negative 6I, 60I.
40J.
Thank you.
And 20K.
Plus R2,
Which is
4I plus 5J negative 2K times
80I plus 40J minus 30K.
minus 30. CI plus 40J minus 30K. Right, so that's it. If you can compute this value of cross product by either distribution or determinant, then all we get is two vectors, the moment generated by vector 1, the moment generated by force 2. Then we add together the vector addition, and then the end result should be this. It doesn't matter what method you use to compute that. The end result should be exactly the same. So let's start doing this guy, right? So in order to do that, I use the determinant. So I, J, A, right? And the first one, 0, 5, 0. The second one, negative 60, 40, and 20. Right? It's going to be I, 0, negative 60, J, 5, 40. All right. So that's going to be I times 5 times 20, 100 I. Plus J times 0 times whatever is 0 plus 0. Minus big parentheses. 5 times 60, negative 300. K plus 0, plus 0, right? That's all. So this is the result of the first determinant. Now we go to the second one. The second one, I'll write it here. I, J, A. And the first one is 4, 5, -2, 80, 40, -30. That's it. We put it here, 5, 4, 80, J, 5, 40. Go ahead and make your diagonals. So here, go ahead, -150, I, -160, J, plus 160K, -400K, -80, I, -120K. That's it. So now we add those two values, two vectors, the output. This plus this is the resultant. The result of all this operation is the resultant. So I write it here. Is equal to 100I, -150. So let's collect all I together. 100, -150. What else? Plus 80. I. So I collected all the coefficients of i's. Now let's go to J. Plus J doesn't have J here. See that? There is a J here, -160. And there is another one, plus 120. 160, negative plus 120. J and plus the coefficients of K. 300 coming from here, plus 160, -400. Times K. So this is equal to 180 minus 150, 30. Positive 30. This guy is equal to -40. This one is equal to 60. Isn't that exactly what we got using moving forces? You see? Now you can agree. That's exactly what we got without doing cross product or method of moving forces. Exactly. Right? So this is the way you do the method of moving force in 3D, three-dimensional application. Now let's go to the section that talks about simplification of force and moments.